Hello, class. I'm sure you're glad to have the test for Chapter 10 out of the way. We now remain with one more chapter. We may not finish all of it, but I think we'll get a fairly good way into Chapter 11. And there's some good stuff in Chapter 11 that'll really help prepare you for future algebra classes, Algebra 2 and Pre-Calc. It'll also help you in geometry as you strengthen your abilities to deal with mathematical equations. So today we're going to be talking about inverse variation. Now, if you recall, we've done a lot of direct variation, specifically linear equations. You remember how many graphs we made when we were making lines, equations of straight lines, y equals mx plus b. I'm sure you remember that stuff. And we had the constant of variation, which was otherwise known as the slope. Remember we talked about slopes a lot? Well, in inverse variation, there are some similarities and some differences. Of course, we still have y equals some function of x. However, instead of direct variation that's linear, we're going to be dealing with inverse variation. So let me jump over here to the whiteboard and let's get started showing you a little bit about inverse variation. Okay. So the first thing I would like to do is just to show you an example. Notice how this graph is. Okay, let me zoom in on it a little bit so that we can see it better. Zoom in like maybe so. So notice, watch the cursor. Notice as we come down, it curves out and approaches y equals 0. This is our y-axis. And if you come down, down, down on the y-axis, you approach to 0. So when x, notice I'm on the x-axis here, my cursor going back and forth on the x-axis. When x is very small, y is very big. And when x is very big, y is very small. That's why you see y coming down, 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 down. This red line is approaching y equals 0. Okay? And the same thing is also true over here. When x is very, very small, or sorry, very, very big, you see that this red line is coming up and it's approaching 0, but it's approaching from the bottom side. It's approaching from the bottom side. And now when x is getting smaller and smaller and smaller and smaller and smaller, coming back towards 0 here, from the negative side, as x is getting smaller, what's happening to y? It's getting more and more negative. It's going farther and farther and farther down. And eventually, you could say that it, for all intents and purposes, approaches x equal to 0 and y will approach infinity. So notice the equation y equals some number, like 50, over x. Now, what would happen if I changed the 50 to 5? Watch the graph when I change it to 5. Okay, it gets tighter down around the origin. Okay, it gets very close to the origin, and if I were to zoom in on this, you can see that it's still the same type of a graph. It's just now that the curve is very sharp and near to the origin. If I make that 500, and let me zoom out here so you can really see the effect dramatically. Hey, what's going on? Hang on. Okay, if I make that 5 to be 500, okay, watch close. That's 50. There's 500. There would be 5,000. The bigger that constant is in the numerator, the farther out the graph goes from the origin, and the curve becomes more gradual and less sharp. Okay? Now, the question is, what happens if I throw a negative sign in front of this? You remember when we had the function y equals x squared? What would happen if we said y equals the opposite of x squared, negative x squared? Then it would flip over. Like, what if y equals 2x squared? Then we know that it would be a little bit linearly stretched, And if we said y equals negative 2x squared, it would be reflected across what? Do you remember? Reflected across the x-axis. So watch what happens here if I throw a minus sign in front of that 5,000. If it's a negative 5,000, watch the graph. Are you watching? Boom. Okay, what just happened? It got reflected across the x-axis. Look at this. Here it is. So look at this section up here on the right. Up here, you see this graph up here? Up here in this first quadrant. If we reflect that across the x-axis, it's just going to flip down in this lower portion, down here, down here, down here. It'll flip over. And this one that's on the left side, in the third quadrant here, it's going to be flipped up into the second quadrant up here. So when I throw the minus sign in front, it gets reflected across the x-axis. So you can see how this works, okay? Okay, reflected across the x-axis. All right, well, I think that's a good introduction. Now, I'm going to take you to the whiteboard, where we're going to do a little bit of work now with actually trying to understand how these equations work. So here we go, over here to our whiteboard. So in inverse variation, basically what we have going on here is as follows. In inverse variation, we have y equals some constant k divided by x. This is the basic form for inverse variation. Y equals some constant k divided by x. And now the example I just was giving you was like 5, 50, 500, 5,000 for k. And you saw what happened to the graph. If k is less than 0, if k is negative, remember, it flips it across the x-axis. It gets reflected across the x-axis, and then we get the second graph that I showed you. So y equals k divided by x. Another way to express this, if we just do a little manipulation, what if I multiply both sides by x? What if I multiply both sides by x? Then I would have x times y is equal to the constant k. X times y equals k. So my constant now would be whatever it is, but the product of x and y must always be equal to that same number. Okay? Always equal to the same number. And no matter which 2 points I pick from the graph, the product of the, no matter which point I pick, the product is always equal to k. So let's take a simple example. Let's take something like 12. What if k equals 12? Then let's make ourselves a little table. By no means are we going to make all of them, but we will make a little table of x and y. So what if x equals to, let's say, 1? If x equals 1, what is y? Well, remember that k equals x times y, and we just said that in this example it's going to be equal to 12. Okay? X times y is going to be equal to 12. Okay? So if 1 times y must be equal to 12, okay, must be equal to 12, then y would have to be equal to 12. Okay? What if I took x equal to 2? Then what is y? 2 times what equals 12? 2 times 6 would be equal to 12. And if x was equal to 3, then 3 times 4 is equal to 12. And et cetera, et cetera. I think you get the picture. So the product of x and y is always equal to the same number. If you know the constant k and you know x or y, you can find the other, the unknown. Because there's 3 things here. There is y, x, and k. We have 3 numbers that we're going to be dealing with. If you know any 2 of those, you can always find the third one. Okay? Now, the thing that's cool here is that k divided by x is always going to be equal to y. And since k is always 12, it doesn't matter which 2 points you have, you will get the same answer. So let me just illustrate here a little bit. Let's call this one x. This would be x1, y1 on our graph. Now let's let this one down here be x2, y2. On our graph, x2, y2. So notice that x1 times y1 equals 12, and x2 times y2 also equals 12. So since they are equal to the same k, since x and y is always equal to the same k right here, then I can say the following. I can say that x1 times y1 is equal to k, but k is also equal to x2 times y2. Now, I hope this is starting to look a little bit like what we did with slopes. Remember, take any 2 points from your linear equation, from your line, from the linear line. Take any 2 points and the ratio. Remember, y equals mx plus b. That m is always the same no matter which 2 points you pick. So you'll get the same values. So it remains constant. So in this case, the k is always constant as well, no matter which 2 points you pick. So we have x1, y1 is equal to x2, y2. So here we go, x1, y1 is equal to x2, y2. This is an important little relationship that you should remember. Don't forget this little guy right here. And of course, what we had a moment ago, I would say this equation right here is very important. You should know this, and I think this one too. These are the things that are most important right now. So y equals k over x, where k is just some constant, and x times y then will be equal to that constant. And since the constant is always the same, x1, y1 will be equal to x2, y2. Okay, let me show you now a little review to remind you about direct variation. You remember that y equals mx. Do you recall that? Y, let me do the following first. Let's review direct variation. It'll look like this. Y equals mx, where m is a constant, the slope. And of course, remember, y equals mx plus b. If we shift it up or down by adding or subtracting a number from it, we're simply translating the graph upwards or downwards. However, the basic form is y equals mx, where m is a constant. We call this direct variation, and of course, it's a little more than just that. It's linear, which means if you were to graph it, it's going to be what type of line? Linear. It's going to be a straight line, okay? It's going to be linear. So y equals mx, and of course m is going to be y divided by x. Y divided by x. So since this is always equal to the same constant for any given line, the slope does not change. That's why it's a straight line. It has the same steepness, if you like, going left to right maybe. What if I said y equals, just as an example, y equals 3x? Then if you were to make this as a graph, you'd have x and y. If x was 0, of course, y would be 0. If x was 1, y would be 3. If x was 2, y would be 6. If x is 3, y would be equal to 9. And if you were to graph this thing, then it's going to be something like so, where it goes straight through there. I'm making a big mess. Just assume that's the origin. Okay, then actually, this is really bad graph. Let me start over. It's supposed to be going through the origin. Just imagine that's the origin. Over 1, up 3. Over 1, up 3. Like that. Over 1, up 3. And sorry, I don't have graph grid here to make it nice for you, but the slope is the same. That's my point. It's over 1, up 3, over 1, up 3. Positive slope, so the lines are going upwards, left to right. Okay? And it doesn't matter which 2 points we pick, the ratio of y to x is going to be equal to the slope. So notice here that 3 divided by 1 is 3. 6 divided by 2 is 3. 9 divided by 3 is 3. So y1 divided by x1 is equal to y2 divided by x2, since they're equal to the same number. So y1 over x1 is equal to y2 over x2. And of course, this is all equal to m. Okay? And you could, of course, use another method as well. You could use your little formula that says that m is equal to y2 minus y1 over x2 minus x1. This is equal to rise divided by run. Okay. Okay, quick review. Just a quick review. So we call this a linear relationship. Linear relationship. Y1 over x1 equals y2 over x2. Okay. Well, it's linear, and this was what we would call a proportion. So something that would work well with this, you'd say something like this. If a car is traveling at a constant rate and you travel 50 kilometers in 1 hour, how far would you travel in 3 hours? Okay, and you'd say 50 is to 1 hour as question mark is to 3 hours. Okay, so you can use a proportion. Now, in the situation that we're working on here, that we're developing, it's not a proportion, but it works in a very similar way. Notice that we can divide both sides right here. We can divide both sides by whatever we'd like, either x2 or y2, go either direction. We could say that x1 divided by x2 is equal to y2, dividing both sides now by y1, over y1. Notice how we did this. We divided both sides by y1, we divided both sides by x2, and we got this relationship right here. Okay? So this is another way you could say x1 is to x2 as y2 is to y1. Notice they're flipped. Personally, I don't think it's best to try to remember this. I think the one that we remember is the one that I've already circled in yellow. I think this is the one you hang on to. x1, y1 equals x2, y2. And then you can solve for any one of the 4 variables there based on knowing the other 3. So if you know 3 of these 4, you can get the 4th one, okay? Through simple algebraic manipulation of multiplying and dividing both sides by whatever number you need to, and you'll get the unknown quantity that you're searching for. Okay, here's an example I'd like to show you. Is this inverse or direct variation? So remember that if it is direct variation, then we're going to have some constant. We're going to have some constant m being equal to y divided by x. That would be direct. Okay, this is direct. Okay. That'll be direct variation. And if it's inverse variation, we're going to have y equal to some constant k divided by x. Or putting it another way, multiplying both sides by x, we get x times y is equal to the constant. Okay? So this would be inverse variation, and this would be direct variation. Which type of variation do we have going on in this table? Notice when x is 1, y equals 2. When x is 4, y equals 8. When x is 8, y equals 16, etc. So does this work? Is it true that x times y is always equal to the same number? Well, let's check it out. 1 times 2, so we can come right here, we can say 1 times 2 equals 2. How about 4 times 8? 4 times 8, does that equal 2? No, 4 times 8 equals 16. Notice we didn't get the same number. This is not equal to this. They're not the same. Okay? They're not the same. They're not equal. So therefore, we do not have inverse variation. Do we have direct variation? Does y divided by x always equal to the same number? So does 2, in the first case, we'll take this one. What's 2 divided by 1? 2 over 1 equals 2. Okay? 8 divided by 4 is equal to 2. And 16 divided by 8 is also equal to 2. Sorry. So notice that these are all the same. And of course, 24 divided by 12 is also equal to 2. So we see that we get the same constant when we divide the two. When we divide y by x, always get the same constant. And that constant is the slope of this line, m. We have a slope of 2. So what type of variation is this? This is direct variation. Direct variation, it's linear, and it's a straight line with a slope of 2. So yes, direct variation is this example. It is not inverse variation. Let's see if we can find another one, work on another one, and see if we can make sense out of this. Okay, so in this example, is this direct or is it inverse? Is this linear? Is it a straight line relationship? Is y divided by x equal the same number? Well, 24 divided by 1 is 24. 12 divided by 2 is 6. 8 divided by 3 doesn't go nicely. You see that the numbers are different. This is not direct variation. Is it inverse? If it's inverse variation, the question is, does x1, y1 equal to x2, y2 equal to x3, y3 equal to x4, y4, etc. Is this going to be true? Well, let's check it out. 1 times 24, is that equal to, question mark, is it going to be equal to 2 times 12? And will that be equal to 3 times 8? And is that equal to 4 times 6? And I think you can see that in each case, these guys are all equal to 24. So the answer is yes. Ka-ching, ka-ching, ka-ching. They are all equal, okay? So therefore, what type of variation do we have going on here? This would be equal to inverse variation, okay? Inverse variation. So the answer is inverse. Variation. It's really hard to write on this screen of this laptop, so just forgive the messiness, but this is inverse variation. Okay, so it works out. And what might that be? What is our constant of variation here? What's the k? Let me expand this question a little bit and ask you, what is k? Remember that y equals k divided by x? Recall that? Y must be equal to k divided by x. And that means y1 equals k over x1, okay? And in fact, you can see here that the k is in fact equal to x times y. K equals x times y, and k then is going to be equal to, k is going to be equal to 2 times 12, 3 times 8, 4 times 6, k equals 24, okay? So writing the equation slightly differently, then y equals 24 divided by x. This would be my equation if you were asked to write the inverse variation equation, or the equation representing the inverse variation. It would be y equals 24 over x. Or equally true, you could write this here. Both are correct. I don't know if there's a preference. I kind of like this one down here myself. I think it communicates a little bit more to me anyway. As x becomes bigger, y becomes smaller. Look at this. As x goes up, y goes down. That's why we call it inverse. As x gets larger, y gets smaller, and vice versa. If x were to get smaller, y would get bigger. Okay? So inverse variation is the answer to this question. So in this example, they say, make the assumption that y varies inversely as x. That's given, I guess you could say. Y varies inversely as x. Now, if that's true, you know that y equals k divided by, remember, if this is true, then y will be equal to some constant k divided by x. Okay? That would be inverse variation. So we're saying if y equals 8 when x equals 4, find x when y equals 2. So cross multiply here, multiply both sides by x if you like, and we get the following. We get that x times y is equal to k, which is, if I can put ones on those, that's also equal to x2 times y2. So let's fill in our numbers now. In fact, let's not fill in our numbers. Let's just do the following. Let's get that k out of the middle, and let's just write this as x1, y1 equals x2, y2. Now you're being asked to find x when y equals 2. You're being asked to find this guy right here, x2, okay? Find x, the new x, x2 if you like, when y equals 2. So let's solve this equation for this guy right here. Let's solve it for x2, meaning get rid of everything else on the right so that you're left with x2. How do you get rid of the y2? Well, you can divide both sides by y2. And so we would get the following. We would get that x2 is equal to x1, y1 divided by y2. Okay? Dividing both sides by y2. So if I were to do that up here, I could show it just by putting a line, putting y2, putting a line, dividing by y2. And notice then that on this side over here, they would cancel out. See, cancel, cancel. And I'm left with x2 equals x1, y1 over y2. Now all you have to do is put your numbers in there and you've got your answer. What was x1? If y equals 8 when x equals 4, so it's 4 and 8, so x1 times y1, 4 times 8, and then we divide all of that by y2, which is 2. And what's this come up to be? 4 times 8 is 32 divided by 2, 16, or 2 into 4 goes 2 times 8 is 16. There you go. X2 equals 16. So this is your answer right here. Okay? Let's see if we can work another equation or solve another problem. Our next example, number 4, comes from the field of optometry. Maybe you'd like to be an optometrist. Inverse variation is used in optometry. When you go to get glasses, the power of the lens that you will be prescribed is described by an inverse variation function. The power of the lens, P, is equal to 1 divided by the focal length in meters. So the power is measured in diopters, okay? We measure power in diopters. Okay? And the focal length, this is defined to be the focal length. Okay, what's happened to my in meters? Now, this is very much a physics problem. You can see physics keeps popping up again and again and again because it is so practical. There are numerous examples around us in life that come from physics. So we often see physics equations in our algebra courses. So here we go. Power in diopters of your lens is equal to 1 divided by the focal length, where the focal length is measured in meters, okay? So the first thing that this example wants us to do is to graph this equation. What does 1 divided by the focal length look like? Well, to answer that, we simply go over here and we have a look at our Desmos graph, and we change this thing to be 1 divided by the focal length. The power equals 1 divided by the focal length, f. And you can see the graph. Right here it is. Inverse variation, typical graph. Notice that we're quite close to the origin. These curves are very close to the origin. Why would that be? Because the constant k is just 1. So this is power in diopters equals 1 divided by the focal length. Okay, so there's the graph. Now the next thing they want to know is the following. They say find the power of a lens with a focal length of plus 0.2. So find the power of a lens with a focal length of positive 0.2. Okay, so we will switch back over here to our whiteboard and work that out. So the question is, what is the power in diopters of a lens with a focal length of, yes, they want a focal length of plus 0.2 meters, 0.2. And 1 divided by 0.2 is equal to 5. Notice that this would be equal to 5 diopters. Okay? 5 diopters, 1 divided by positive 0.2, focal length of 0.2 meters. The next question says, what if it was negative 0.4 meters, the focal length of this lens? What would be our power in diopters? Okay? What would be our power in diopters here? Not quite sure why this thing keeps messing up on me. Here we go. So that's the first one. And what is the power if, in fact, the focal length was negative 0.4? Okay. Then what would the power in diopters be? Well, 1 divided by 0.4. 0.4 goes in 2.5 times, but it's negative. So this would be negative 2.5 2.5 diopters. Negative 2.5 diopters. So there you have an example that came from optometry. So power of lenses, focal lengths, and understanding what is a diopter. 1 divided by the focal length. Very good. Let's look for another example. Okay, we're going to pick this up again and do another example. So I've written this out for you. When under equal tension, the frequency of a vibrating string in a piano varies inversely with its length. If a string is 420 millimeters long, and if it vibrates at a frequency of 523 hertz, or cycles per second, or hertz is a cycle per second, at what frequency will a 707 millimeter string vibrate? Okay, so frequency is inversely related to, varies inversely with the length. So how would we write that? First of all, let's see if we can make a little equation to get us going. Frequency is inversely related to the length L. Okay? Frequency varies inversely with the length. So that means that if we multiply both sides by L here, if I do this, then what happens? These L's cancel, and so I have L times F, or F times L, is equal to K. So I can then say that F1 times L1 must be equal to F2 times L2. Now notice the thing that is mentioned here at the bottom. The diameter and the composition of the two strings are the same. So we have two strings, exactly the same diameter, exactly the same materials, and we stretch them to exactly the same tension, but we have two different lengths. So the first one is 420, vibrates at 523, and the second one is 707, and the question is, at what frequency will it vibrate? So we're looking for, what would you say we're looking for? F1 or F2? We're looking for F2, second frequency. So they give us the first set of data, then they said at what frequency will a string of 707 millimeters vibrate. So we take this little equation and we solve it for F2. F2 is going to be equal to F1 L1 divided by L2. I'm dividing both sides by L2. F1 L1 divided by L2. And so frequency number 2 is going to be equal to frequency 1. What was the first frequency? Coming back up here. First frequency was 523 at 420. So 523 hertz times 420 millimeters divided by 707 millimeters. Notice the millimeters cancel. If we're looking at units, the units cancel there, and so we're left with an answer of hertz, which is exactly what we need. So what does F2 come out to be? The frequency of the second string will be equal to the result of this computation, which I will now solve. And the answer is 310.69. 310.69 hertz. Okay, and this little guy up here was supposed to be hertz as well, which didn't come out very clear. A hertz is a cycle per second. One complete cycle of a wave in every second. So that's, or one cycle of a wave per second is 1 hertz, and this is 523 cycles per second, and the second wire has 310.69 cycles per second. So that's your answer. Here we go. 310.69. So here's another example for you. Example number 6. I think this will be the last one we do today. Again, y varies inversely as x. Okay, y varies inversely as x. You know what that looks like. That means that y equals some constant divided by x, which when rewritten, it means that x times y is equal to the constant k. Okay, so now it also means then that x1, y1 is equal to x2, y2. So if y equals 1/5 when x equals negative 20, then find y when x equals negative 8/5. So find y when x equals negative 8/5. That means we're looking for the second y. We're looking for this guy. So we divide both sides by x2, and we will have y2 by itself. So let's divide both sides by x2, and here's what we get. We get that y2 is going to be equal to y2 is going to be equal to the following: x1, y1 divided by x2. Which will be equal to then, what is x1? Negative 20. Times y1, 1/5, divided by x2, which is negative 8/5. Okay, negative 8/5. So let's do the top, and then we'll do the bottom. How many times does 5 in the numerator now? How many times does 5 go into 20? It goes 4 times, doesn't it? So 1/5 of 20 is going to be 4, but it's negative 20. So the numerator is going to be equal to negative 4. Numerator, negative 4. So this is going to be equal to, I'm going to go back to red here. The numerator is going to be as follows. It's going to be equal to negative 4, and we're going to be dividing that by negative 8/5. Now, do you remember your rule for dividing fractions? What do you do when you're dividing by a fraction? Okay. You invert and you multiply. So this will be equal to negative 4 over 1. And I don't like the way I'm writing this. It doesn't look right. Let me do it carefully. This is going to be equal to, still not doing it right. Hang on. This is going to be equal to negative 4 over 1. And we're going to be multiplying that by negative 5 over 8. We invert and we multiply. And then we can say, well, 4 goes into itself 1 time. 4 goes into 8 2 times. So how does this thing work out in the end? It's going to be equal to a positive, because a negative times a negative is a positive, positive 5 over 2. Okay, that's y2. So there's your answer to your last problem there that we have done. y2 equals 5 halves. 5 halves. So I hope that this was sufficient to give you a good understanding of inverse variation. If you have any questions, as always, you're free to WhatsApp me or send me an email or a message through Moodle. However, Moodle, I don't check Moodle all the time. So if you really want to get a hold of me, I suggest you send me a WhatsApp message or just call me through WhatsApp. Calling is probably a little more sure because I'm more likely to hear the phone go off. So in any event, best of luck to you as you do this next assignment. Work hard. Finish strong. We are close to the end, but we're in important material right now. It's very valuable for you to know, so study hard, don't get discouraged. I've tried to lighten the pace a little bit so that you won't be under so much stress. The danger of that is you might just relax, and I think maybe a few of you have relaxed more than you should have, and some of your exam scores showed that for 2 or 3 of you. I was quite disappointed in some of those exam scores. Step it up, eh? You have one more test to go, and make it count. Do really, really well. And the way you'll do really well is every day, do your homework, study, watch the videos, and watch the videos again. Watch them more than once. Take notes on the videos, okay? Take a little notepad, write down everything that you've learned in those videos, write down the examples. And that way you won't have to necessarily watch through them all again. You can just quickly review your notes, and you should be good to go. So, all right. Talk to you next time. You guys have a good evening.